In 1998, two rival teams of astronomers set out to measure how fast the universe's expansion is slowing down. It isn't slowing down, it is speeding up. Every distant galaxy is being carried away faster with every passing year, as if gravity, on the grandest scale, had been thrown into reverse. Whatever is doing the pushing makes up about 2/3 of everything there is. It outweighs every star, every galaxy, and all the dark matter combined. We call it dark energy, we can measure it, and a quarter of a century later, we still cannot tell you what it is. This is the story of the biggest thing in the universe. To measure the fate of the universe, you first need a candle. The two teams, one led by Saul Perlmutter, the other by Schmidt and Riess, chose the brightest candle nature makes, a Type 1 supernova. It happens when a dead star called a white dwarf steals matter from a companion until it reaches a critical mass and detonates. Same trigger, same critical mass, so the explosions reach nearly the same brightness anywhere in the universe. The fainter one looks, the farther away it is. Both teams hunted these explosions across billions of light years, expecting to watch the expansion slowing under its own gravity. The rivalry was fierce, and in 1998, both arrived at the same impossible answer. The distant supernova were too faint, too far away. The expansion of the universe was accelerating. Hold on to what that means. Since the Big Bang, space itself has been stretching, carrying the galaxies apart like raisins in rising dough. And everything we knew said the stretching must slow, because the universe is full of matter and matter pulls. An explosion coasts, gravity breaks. The only question was how hard the brakes were pressing, because that answer decides how the universe ends. Instead, the supernova revealed that roughly 5 to 6 billion years ago, around the time our sun was forming, the braking ended. The universe pressed the accelerator. Space is not just expanding, the expansion itself is gaining speed. Something inside space is pushing outward, and on the largest scales, it is beating the gravity of everything. In 2011, the discovery won the Nobel Prize. The explanation is still missing. This is no small correction at the edge of the data. The same cosmic recipe keeps being read from completely independent measurements. The ripples in the cosmic microwave background, the oldest light in the universe. The pattern of the galaxies themselves, frozen ripples of sound from the Big Bang used as a cosmic ruler, and the supernova, 3 different methods. One answer: ordinary matter, everything you can touch, about 5%. Dark matter, about 27%. We told the story of that missing matter in our last episode. This is the bigger slice. Dark energy, roughly 68% of everything there is. Put all the matter in existence on one side of a scale, every star, every planet, all the dark matter, and the push outweighs the lot, 2 to 1. So what could it possibly be? Start with what it is not. Dark energy is not dark matter, they could hardly be more different. Dark matter pulls. It clumps and builds the scaffolding of galaxies. Dark energy pushes and it clumps nowhere. As far as we can measure, it fills space perfectly smoothly, the same in every direction, the same everywhere, and it is unimaginably dilute. In a cube of space, a meter on each side, dark energy amounts to roughly the energy of a few atoms of hydrogen. So how does something that thin dominate the cosmos? Because it is everywhere, even in the emptiest voids, and because, unlike matter, it does not thin out as space expands. Matter dilutes. This does not. Every new stretch of space arrives carrying its share of the push. Give it enough room, and the faintest whisper becomes the loudest voice in the universe. Here is the strangest part. The leading explanation was written down 80 years before the discovery by Albert Einstein. In 1917, his new theory of gravity kept insisting the universe must move, grow, or shrink, while every astronomer swore it stood still. So Einstein added a patch to his equations, a constant, a faint outward pressure woven into space itself, tuned to hold the cosmos in place. Then Hubble showed the universe was expanding after all, and Einstein struck the term out, reportedly calling it the greatest blunder of his life. For 70 years, the constant sat there like a ghost. Then came 1998, the acceleration, and physicists reached for the one term that fit. Einstein's blunder came back as the best description we have of 2/3 of the universe. Then they asked what could put that constant there, and the answer broke physics. Quantum physics says empty space is not empty. At the smallest scales, the vacuum seethes, fields trembling, particles flickering in and out of existence. That restlessness carries energy, and energy woven into space itself would do exactly what dark energy does: push. It sounds like a solved case. It is not market open, because when physicists estimate how much energy the vacuum should hold, the answer comes out too large, not by a factor of 10, not by a million, by up to a 1 followed by 120 zeros. It has been called the worst theoretical prediction in the history of physics. If the vacuum really pushed that hard, space would have torn itself apart before a single atom could form. No galaxies, no stars, no you. The fact that you exist proves the prediction wrong, and nobody can tell you why. So the suspects multiply, and every one of them is unproven. Perhaps dark energy is not a constant at all, but a field, an invisible ocean filling space with its own slow currents. Physicists call it quintessence, the fifth element, after earth, water, air, and fire. A constant is locked forever. A field can drift, strengthen, decay, or perhaps nothing fills space at all, and the mistake is gravity itself. Perhaps Einstein's equations. Flawless in every test, we can run close to home, bend at the scale of the whole cosmos, and the acceleration is a misreading of the law. Every one of these ideas is alive. None is confirmed. But notice what separates them. A constant never changes. Almost everything else does. So measure the push across cosmic history and see whether it is changing. That measurement is happening right now. On a mountaintop in Arizona, an instrument called DAISY, 5,000 robotic eyes sharing one telescope, is building the largest map of the universe ever made. Millions of galaxies and quasars reaching 11 billion years into the past. Buried in that map is a ruler. Sound waves that rippled through the newborn universe left a faint imprint on where galaxies gather, a preferred distance, stretched ever larger as space expands. Read that ruler at different ages of the universe, and you can reconstruct the whole history of the expansion, a biography of the push. If dark energy is Einstein's constant, the biography will be flat. The same push, at every age, forever. Any wobble in that line means new physics. In 2024, the first results arrived, and they carried a whisper. Combine DAISY map with the supernova and the oldest light, and the data fits slightly better if dark energy is not constant, if the push was stronger in the past and is weakening now. In 2025, with 3 years of data, the whisper grew louder. Be careful with this. It is a hint, not a discovery. The signal still sits below the threshold physics demands. And hints this size have dissolved before. It may yet vanish, but if it holds, it would be revolutionary. A constant is a property of space. A changing push is a thing with dynamics, a history, and a future. It would be the biggest crack in our picture of the cosmos in a generation, and it would reopen a question we thought we had answered: how the universe ends. We have told that story on this channel, the heat death. The stars gutter out, the black holes evaporate, and the cosmos fades over unimaginable spans of time into cold and even silence. But that forecast quietly assumes dark energy is constant. If instead it strengthens with time, the ending is not a fade, it is a tearing. Galaxies unbound, then solar systems, then planets, and in the final fraction of a second, atoms themselves, the big rip. And if dark energy weakens, as the new hints whisper, the acceleration could ease, or, in some models, reverse, letting gravity gather everything back into a big crunch. Freeze, rip, crunch, 3 endings, and the choice hangs on the one ingredient of the universe we understand least. The fate of everything is written in dark energy. We cannot yet read the handwriting. So here is where the case stands. That the expansion is accelerating, established beyond reasonable doubt, confirmed by every method we have. That dark energy makes up roughly 2/3 of the universe, measured again and again. What it actually is, a constant Einstein wrote and regretted, an evolving field, a flaw in our law of gravity, remains open. It may be the most precisely measured ignorance in science. We can state, to the percentage point, how much of reality we do not understand. And the answer is being written now, one galaxy at a time. So let me leave you with the question the universe will answer one day. Is dark energy constant, the same quiet push forever, or is it changing, and with it, the ending of everything, constant or changing? Tell me what you think in the comments, and I'll see you in the deep field.